Okay. All right, so now we're going to tackle combination circuits. Now, combination circuits are circuits that are neither strictly parallel nor neither strictly series. Like for instance, this pathway here is obviously in parallel with this pathway because they both leave at this junction and come back at this junction. Yet on this parallel path, there are two resistors in series. And moreover, on this pathway, we have a battery and two resistors in series. So as you can see, we cannot apply the rules of parallel or series in a simplistic manner to this circuit. So to solve these circuits, we use what is called Kirchhoff's laws. A real quick review of what they are again. Okay, let's start with the easiest one, Kirchhoff's current law. Kirchhoff's current law says if you have a junction, which is kind of like a fork in the road or an intersection in traffic, the currents going into the junction have to leave the junction. So in this particular example, I have 1 amp, 5 amp, and 10 amps going into the junction. So a total of 16 amps going into this point. Current cannot stick around. Current is always flowing. So that means we have 16 total amps leaving the junction. That's just an example. So Kirchhoff's current law says current in must equal the current out. All right, real simple. Kirchhoff's voltage law says that you pick any loop that goes with the flow, and you'll get this rule that says the voltage of the battery must equal the voltages of each resistor. It's very similar to a series circuit, except you have to pick a path and it has to be a closed loop. In fact, I should add that word here, closed loop. So you have to start at the battery and you go with the flow. So if I go this way and I go through this resistor, that's the first voltage drop of this pathway, okay? When I get to here, I have to pick this path or this path. Let's say I go this path, all right? Still going with the flow. And then I get another junction, I go with the flow. So that is an example of a loop. Well, that loop is going to obey this law. The voltage of the battery will equal the voltage drops of those three resistors, irregardless of what these voltage drops are. So with that, we're going to build a system of equations that will help us solve the question, how will current flow in this particular circuit? Well, current is going to come out of the battery. We like to signify conventional current as leaving the positive end. I'm going to call this current 1, right? It's the current leaving the battery. Current 1 is also the current that goes through this resistor. Also, the current going out of the battery is the same amount of current that goes into the battery. So that's also current 1, which means current 1 was also the current going through that resistor. Here at this point, I have a junction. Some of the current will get to this junction and decide to flow down this path, and some current will decide to flow down that path. I'm going to say that this path is path 2, we'll call it, and that's going to be current 2. And then down this pathway, we're going to have current 3. And current 3 is going to go through both of those resistors in series, because 2 resistors in series get the same current, and current 3 gets back here. All right, current 2 is going to flow through this resistor. So in sum total, we figured out that there are 3 unknowns: the current in pathway 1, the current in pathway 2, and the current in pathway 3. This means we have 3 unknowns that we're going to have to build 3 equations in order to solve for these 3 unknowns. And we're going to do that using Kirchhoff's laws. So let's start off with Kirchhoff's law. I pick a junction. I'm going to call this junction A. So Kirchhoff's current law at junction A says that current 1 is going to split up, that's what's coming into the junction, into 2 currents. So all of current 1 is going to equal the summation of current 2 and current 3. Okay, that's equation number 1. One might think, oh, look, I can do another Kirchhoff's current law here at this junction. But you can't, because it would give us the same exact equation. I2 plus I3 would equal I1. So we're done with Kirchhoff's current law. That means we have to go now to Kirchhoff's voltage law. So Kirchhoff's voltage law is for a loop. So let's do a loop from the battery. Remember, you must start from the positive of the battery, and you go with the flow. So here we go, I'm going to go with the flow. And when I get to this point, I can go down this path or that path. Let's just do the first path. Okay, so I'm going with the flow until I get back to the battery, and that's my loop 1. Okay, so the battery voltage is 36 volts. Okay, that's all of the batteries on this loop. The first voltage drop is at this resistor. Now, we all know that voltage, I broke my pencil, I'm gonna pause the video, resuming the video with my new pencil. Okay, we all know that V equals IR, correct? So if I wanted to calculate the voltage drop at that resistor, I would take its current and multiply it by its resistance. That's how you find voltage, right? So what I'm going to write here is the voltage drop is going to be 10 ohms times I1. Right? That's my first voltage drop. Okay, my next voltage drop on this path is I2 going through 15 ohms. So I'm going to add that voltage drop. And then I'm going on the loop, and now we have my next and final voltage drop, which is I1 times 2 ohms. Okay, now I have 2 equations. Now I can simplify this equation by combining like terms. That's what I'm going to do right now. 36V. We have 2 I1s, so I have 10 plus 2 is 12 ohms times I1 plus 15 ohms times I2. Okay, now let's do our next Kirchhoff's voltage law. It'll be loop 2. So I have to once again start at the battery and go with the positive end. And I'm going to go through here, but now I'm going to go along this path back to the battery, right? It's going to be my loop 2. All right, so let's go. All right, the battery is still 36 volts. First voltage drop, just like the first circuit, 10 ohms times I1. But now I'm going along this highway with current 3 going through 2 resistors. Okay, so I'm going to have 5 ohm I3. And I have 2 of those, so I might as well just multiply that by 2. Okay, continuing along the path. And I'm going through this resistor again, 2 ohm I1. All right, that's my loop 2. These are like terms. So simplifying that, I have once again 12 ohms times I1 plus I had 2 5-ohm resistors. Basically, I had 10 ohms times I3. I have 3 equations and 3 unknowns, and I can use these 3 equations to solve for those unknowns. I'm going to write them together, and I'm going to kind of line them up. So I'll start with the voltage laws, right? So I'm going to have 36 volts equals 12 ohm I1 plus 15 ohms I2. And then I'm going to add that I have 0 I3s on that path. And I can do that. I can add 0. It doesn't change the equation. All right, Kirchhoff's second law. For the second loop, I mean to say, 12 ohm I1s. And I have no I2, so I'm going to write I have 0 I2s. And I have 10 ohms of I3. The reason why I write it this way is so that all my I1s line up, all my I2s line up, and all my I3 lines up. How do I get to do that using Kirchhoff's current law? Well, to do that, I need to bring the I1 to the other side. So literally, I could write 0 equals, first of all, I have I2, plus I3, right? And then I'm subtracting I1. I have a negative I1. There's no difference between this expression and that expression. Now I'm going to add some coefficients here. And there's my system of 3 equations. At this point, you can do substitution. Use your calculator to graph 3 lines. But that's going to be complex. What I would rather you do is do it with matrices. And that's going to be in my next video.